This video is about section 11.4 and it is about the binomial probability. And there are two objectives we're going to cover: to construct a simple binomial probability distribution and to apply the binomial probability formula for an experiment involving Bernoulli trials. Now, the constructing a simple binomial probability distribution, I would highly encourage you to study this in the book. There's a very good example that explains it in all detail, and you can go over it again, but so you have an understanding what that is about. And what I intend to do here in section 11.4, to go over the formula, do some demonstrations of how to use it. But it's really based on the fact that you read the section 11.4, follow the examples, and then it'll be easier for you to follow the examples that I'm doing here. So here's some definitions. Bernoulli trials, for example, the repeated performances such an experiment where the probability of success remains constant throughout all repetitions are known as repeated Bernoulli trials. So that's one of the important things about this formula coming up in just a moment. Also, there's a formula that you need to know. The number of combinations of n things taking r at a time is n factorial divided by r factorial times n minus r factorial. I hope that you have a working understanding of what factorial means. So n factorial means n times n minus 1 times n minus 2 times 2 times 1. For example, to compute 6 factorial, there would be 6 times 5, 6 minus 1, times 4, 6 minus 2, times 3, times 2, times 1. And just to let you know, in case you are using an iOS device like an iPhone or something, the calculator that's in there, if you have it in landscape mode, then it looks like this. And it has a factorial key here in the lower left-hand corner. Let me just point that out with a pen. So all you need to do is input, let's say, the number 6. So 6 is there. And then press the factorial button. And you have the answer as 720. Or, of course, you can do the calculations manually, but either way, the answer is 720. It's a very rapidly growing function. For example, 12 factorial is not 2 times 6 factorial, but let's just do it. 12. So we input 12 and we tap the factorial button and we find out it is 479,001,600. So 479,001,600. So it's a very rapidly growing function. One thing you need to know about a particular detail, and that is that 0 factorial is defined to equal 1. So that's a definition. And the reason you need to know it, because sometimes when you apply the formula, like in this one here, then you wind up with 0 factorial in the denominator at times. For example, when r equals n, then obviously you have 0 factorial in the denominator, and that is equal to 1. So in other words, that's an important detail to remember when it comes to actually applying this combinations formula here. So again, this stands for the number of n items, the number of combinations of n items taking r at a time. So Which brings us to the binomial probability formula. It's a very important formula. We'll be using it several times here in this section. And here's how it goes. When n independent repeated trials occur, where p is the probability of success and q is the probability of failure, and remember that q is always equal to 1 minus p in this context here, then remaining constant throughout all n triads. So that's an important detail, that the probability of success and failure remain constant throughout all the triads. Then the probability of exact x successes is calculated as follows. The probability of x equals the number of combinations of n things taking x at a time, p to the x power times q to the n minus x power. So then in the expanded version, that is n factorial divided by x factorial times n minus x factorial in the denominator times p to the x times q to the x minus 1. This may look a little bit daunting, but as we go through some examples, you find it fairly easy to follow this, but you have to be somewhat detail-oriented. Okay, but this is a formula, and so you may even want to memorize it. How about that? Let's do some examples with the binomial probability formula applied to a rolling dice. A fair die is rolled 3 times. A 4 is considered success, while all other outcomes are failures. Find the probability of each number of successes. So to apply the formula, the probability of x equals the number of combinations of n items taking x at a time times p to the x times q to the n minus x. What we need to do to apply this formula, we need to find out what is n, what is p, what is q, and what is x. So since n and p are the same for all the examples here, we're talking about n being equal to 3. There are three dice are rolled 3 times, so 3. And the probability of rolling a 4 is 1/6, because there are 6 sides to a die, so the probability of a 4 showing is 1/6. And then the probability of failure would be 5/6. So these numbers are the same for all 4 examples. For the first one, for number 23, x is equal to 0. So then the probability of no 4 showing would be equal to the number of combinations of 4, 0, and then p is 1/6 to the 0 power. It was to the x power, right? So the 0 power times 5/6 to the let's see, the 3 dice would be 3. Sorry about that. Minus 3 minus 0 power. And so that means this expanded would be 3 factorial divided by 3 minus 0 factorial times 0 factorial. And then 1/6 to the 0 power is 1. And then we have 5/6 to the 3rd power. Now, this expression is then 3 factorial divided by 3 factorial. And since 0 factorial is 1, 3 factorial divided by 3 factorial is 1 times this 1 here. And 5/6 to the 3rd power would then be 1 times 1, and 5 to the 3rd is 125. and 6 6 to the third power is 216. So that is the probability of no 4 showing up when you roll the dice. For number 24, we have a similar approach to 24. We want to know the probability of 1 4 showing up. So it would be the combination of 3 things taken one at a time times 1 6 to the first power times 5 6 to the 3 minus 1. And so this would be 3 factorial divided by 3 minus 1 factorial times 1 factorial times 1 6. And 3 minus 1 is 2, so that's 25 divided by 36. This then would be 3 times 2 times 1 divided by 3 minus 1 is 2 factorial, which would be 2 times 1 times 1. And so that would be equal to 3, well, times 1 6 times 25 divided by 36. So then these cancel. And so then finally we have 25 divided by 72. Okay. And number 25, very similar. I'm going to leave out a couple of steps now because I like for you to do them yourself also. But the probability of 2 4 showing would be the number of combination of 3 things taken 2 at a time would be 1 6 to the second power times 5 6 to the 3 minus 2 power, and that would be equal to 3, that's what this expression is, times 136 times 3 minus 2 is 1, so it would be 5 6. And that's equal to 5 divided by 72. And then for number 26, the probability of 3 4s showing when we have 3 dice would be the combination of 3, taking 3 at a time, times 1 6 to the third power times 5 6 to the 3 minus 3 power, and so that would be equal to, this is equal to 1. And 1 6 to the third power would be 1 divided by 216. And 3 minus 3 is 0, and 5 6 to the 0 power, any real number other than 0 raised to the 0 power is equal to 1. So remember, a to the 0 power is equal to 1, as long as a is not equal to 0. Okay? So remember this one about exponents. So then the answer is 1 divided by 216. So that is the answer for number 26. The next exercise is about the side effects of prescription drugs, and it is known that a certain prescription drug produces undesirable side effects in 35% of all patients who use it. Among a random sample of 8 patients using the drug, find the probability of each event. So again, we need to set up the basics here. So because we're talking about 8 patients, so we know that n is equal to 8, and 35% use them have side effects, so p is equal to 0.35. That means that q is 1 minus 0.35, which means it's equal to 0.65. And so now as we look at the requirements here, we are supposed to find the probability of each of the events. Like for number 39, is none has undesirable side effects. So that means in this case, then x is equal to 0. So we're looking for the probability of p of 0, which would be the number of combinations of 8 with 0 here. And then that's 0.35 to 0 power times 0.65 to the 8 minus 0 power. And when we multiply that out, that is equal to 0.032. Okay, now for the next question, exactly 1 has undesirable side effects. So it means x equals 1, so the probability of 1 would be then the combination of 8 things taken one at a time times 0.35 to the first power times 0.65 to the 8 minus 1 power. And when we calculate that probability, we find it's 0.137. And then for number 41, the question is exactly 2 have undesirable side effects. So now we're looking for the probability of x equals 2. So it'd be the combination of 8 things taken 2 at a time times 0.35 to the second power times 0.65 to the 8 minus 2 power. And when we multiply that out, we get 0.255. Number 42 asks us to compute the probability that more than 2 have undesirable side effects. So here we're asking the probability of x greater than 2. That means the probability of 3 having side effects plus the probability of 4 having side effects, etc., until you get to the probability of 8 having side effects. Or we can use the complement and say that's 1 minus the probability of x less than or equal to 2. So that means 1 minus the probability of 0 side effects plus the probability of 1 with a side effect plus the probability of 2 having side effects. And since we already have the numbers for these probabilities, we simply write it as 1 minus 0.032 plus 0.137 plus 0.255. So that's equal to 1 minus 0.428. So our final answer is 0.572. So in this case, it was very advantageous to use a complement rather than doing it directly, even though you could do it directly. In fact, if you use technology, you can do this as one setting on your calculator, like TI-84 or something similar. So, and by the way, I did that and double checked the answer, and it's correct, no matter how you do it. The next exercise requires a little bit of thought, and that's called taking a random walk. Abby is parked at a mile marker on the east-west country road. She decides to toss a fair coin 10 times, each time driving 1 mile east if it lands heads up, and 1 mile west if it lands tails up. And then there's an explanation about random walk, and we can leave that out. So, but let's talk about the exercises. And each of the exercises, 50, I only did 52 to 58, find the probability that Abby's walk will end as described. So let's think about what this is about. So let me draw the country road. So here's the country road, east and west. Here's where she starts. And here's the miles to the right, towards the east, and miles to the left, go to the west. So let's think about one particular example, number 52. Find the probability that Abby's walk will end as described, or drive as described, 6 miles to the east of the start. So to end up at 6 miles east, think about what that means. With 10 coin tosses, that means she needs to have 8 heads and 2 tails to go back. Okay, 8 successes, heads rather, and 2 tails. So if she does 8 heads and 2 tails, she winds up at the 6 mile marker. So in other words, we're asking for the probability of 8 heads, and so here for all of the examples, n is equal to 10, and the probability of heads is 1/2, and the probability of tails, q in other words, is also 1/2. So this is the same for all the exercises here in the context of this problem. So then P of 8 would be equal to the combination of 10 things taking 8 at a time, and 1/2 to the 8th power times 1/2 to the 10 minus 8 power. So and this combination of 10 things taking 8 at a time, that's equal to 45 when you evaluate that. And this is simply 1/2 to the 10th power. So there would be then 45 divided by 1024. 1/2 to the 10th power is 1024 times 45 would be this number here. And in decimal format, it is 0.044. Okay, now for the second one, winding up 10 miles east, she needs to have 10 heads in a row. So the probability of 10 heads in a row is simply 1/2 to the 10th power, and that's 1 divided by 1024. And in decimal form, that's 0.001 approximately. Now we talk about the next one, number 54, 5 miles west of the start. Again, she starts here. And how can she get to 5 miles west? Well, if she has let's say, 7 heads, or 7 tails rather, that means she has 3 and 7, hold on, 7 tails, then she has 3 heads. So 7 minus 3 gets her to 4. If she has 8 tails, that means she has 2 heads, and that ends up on 6. So in other words, there's no way she can ever wind up at the 5-mile marker or 5 miles west. So that probability is 0. She cannot do that. Now, 6 miles west of the start, that means she has to wind up with 8 tails and 2 heads, which is exactly the same probability that we had before. So again, it's probability of 8. And since the probability of heads and tails is the same, the probability, of course, would be the same. So it is 0.044. Same probability. And now at least 2 miles east of the start, that's a little bit more complicated. Because here we have to think about the different probabilities that we need to add up. So the probability of x being greater than or equal to 2 would be the probability of 2 miles, being at 2 miles, plus the probability of being at 4 miles, and the probability being at 6 miles, plus the probability of winding up at 8 miles, plus the probability of winding up at 9 miles, plus the probability of being at 10 miles. The reason why I'm leaving out the 3 and the 5 and the 7, is because for the same reason we cannot get to 5, we cannot get to 1. Because when we have, let's say, 9 heads, or let's say 5 heads, that means we have 5 tails. But when we have 6 heads, that means we have 4 tails. It gets us to 2. So we cannot get to 1. In a similar way, we cannot get to 3 or 5, and we cannot get to 7 either, but we can get to 9. And that's by having 10 heads, I'm having... So here are the probabilities we need to figure out. Now to get to 2, we need to have 6 heads and 4 tails. So 6 heads means we need the probability of 6. And to get to 4, we need the probability of 7 heads and 3 tails. 7 minus 3 is 4. And to wind up at 6, we need to get the probability of 8 heads, because that means we have 2 tails, and 8 minus 2 is 6. And to get to the probability of 8, to get to mile marker 8, we need to have 10 minus, we need to have 9 minus 1. That'll get us to number 8. And then the probability of 10, we already know how to do that. That's 10 heads in a row. So these are the probabilities. So that means for the probability of winding up at 6, it's a number of combinations of 10 items taken 6 at a time, 1/2 to the 6th power times 1/2 to 10 minus 6, or to the 4th power. So as you may have noticed, this always adds up to 1/2 to the 10th power. So therefore, I'm not going to rewrite it every time how that breaks up with the exponents. It's always 1/2 to the 10th power. So here we have the number of combination of 10 taken some at a time, and then for the 8, to get to the 8, we have the combination of 10 taken 8 at a time times 1/2 to the 10th power. And then for number 9, for the 9s would be the combination of 10 taken 9 at a time times 1/2 to the 10th power. And then finally, the last one would be the combination of 10 taken 10 at a time times 1/2 to the 10th power. And so that means this is now equal to this expression is equal to 210 times 1 over 1024. That's 1/2 to 10th power, plus 120 times 1 over 1024. So that's equal to 120. That's 210. And this expression is equal to 45. 45 times 1 over 1024 plus 10 times 1 over 1024 plus 1 times 1 over 1024. So then that's equal to 210 plus 120 plus 45 plus 10 plus 1, all divided by 1024, and that is equal to, so that's equal to 386 divided by 1024, and in decimal form it is 0.377. So that was number 56. And number 57, 2 miles east of the start, well, we already calculated that as a probability of P of 2. In other words, you have to get to 6. And so that was 210 times 1 over 1024. So that's 210 divided by 1024, since we did that calculation in conjunction of number 56. And that's equal to 0.205. And to be exactly at the start, to wind up exactly at the start, she would need to have 5 heads and 5 tails. So it's P of 5. And there would be the combination of 10 taking 5 at a time times 1/2 to the 10th power. And there would be 252. So it's 252 divided by 1024 for number 58. And that's equal to 0.246 in decimal format. So some of these exercises can be a little bit complicated, especially number 56, at least 2 miles east of the start. And so you have to think things through how you can wind up at the various points along the east and the west direction. The next exercise is a little bit easier, a little bit more straightforward. It has been shown that 60% of a certain group of people have brown eyes. Find the probability that among 9 of these people, each number will have brown eyes. So again, we're dealing with the binomial probability distribution. The probability of x equals the number of combination of n things taking x at a time, p to the x power times q to the n minus x power. Okay? So in this case, n for all these exercises, n is equal to 9, and p is equal to 60%, so 0.6. It means that q is equal to 0.40 or 0.4. Okay? So then for exactly 4, for number 43, we have probability of 4 is equal to the number of combination of 9, 4 at a time, times 0.6 to the 4th power, times 0.4 to the 9 minus 4. We're going to write it out this time. And so that is then equal, when we multiply this out, that is equal to 0.167. Now for the next one, number 44, from 4 to 6, there would be the probability of 4 having brown eyes, plus the probability of 5 having brown eyes, plus the probability of 6 having brown eyes. So so that's equal to 0.251, and then the probability of 6 having brown eyes is equal to the number of combination of 9 taking 6 at a time, 0.6 to the 6th power times 0.4 to the 3rd power, and that turns out to be the same, 0.258. So then, since you already know what P of 4 is, the probability of 4, 0.167 plus 0.258 plus 0.258. So our answer is 0.669. Oops. So that's a 9. 0.669 for number 44. And for number 45, the probability that all 9 have brown eyes in this group of people, it would simply be 0.6 to the 9th power, and that is equal to 0.01. And then the probability of at least 3. So that is the probability of x greater than or equal to 3. So that means we add up all the probabilities for having 3 brown color plus probability of 4, etc., up to P of 9. But we might be better off if you look at the complement and use 1 minus the probability of x less than 3. And so that would be equal to 1 minus the probability of x equals 0 plus probability of x equals 1 plus the probability of x equals 2. Oops, there's a p missing, plus. Okay. So when we compute these probabilities, it would be, the number of combination of 9 taken 0 at a time, of 0.6 to the 0 power times 0.4 to the 9th power, plus the combination of 9 taken 1 at a time times 0.6 to the 1st power and 0.4 to the 9 minus 1 or to the 8th power, plus the combination of 9 taken 2 at a time, that would be 0.6 to the 2nd power times 0.4 to the 9 minus 2 or 7th power. And that would be equal to 1 minus, as we evaluate each one of these expressions. The first one would be 0.00026. And the second one would be 0.00354. And the last one, this one here, is 0.0212. So that's equal to 1 minus, when we add up the terms in the brackets, 1 minus 0.0251. So the final answer then is 0.975. Checking with technology, adding up all possibilities from P of 3 to P of 9 gets the same result. But if you do it manually this way, it's easier to use a complement. So that's what we did here in this example. So let's write the final answer here. For at least 3, the final answer was 0.975. So I hope this was enough information for you, so you can do this on your own, and good luck. This is the conclusion of section 11.4.